All right, guys, well, welcome back to the last section of chapter 1.4. We're going to use all those definitions that we started implementing and discussing for all of those trig functions that we introduced last week. But if I'm going to mention anything at the end of this chapter 1, as we bleed into chapter 2 is probably the most important chapter that we can, of the 8, put our finger on and say, without this, the rest of it doesn't really work. So really work hard this week. Make sure that you guys are paying attention to all the little details and things, and memorize as much as this as you possibly can, because the more you memorize, not only the faster, but the easier things will be for you in the near future. Okay? So we're going to start off with using these definitions. And as you can see here, we've already define them in terms of the x and the y and that r radius that we talked about to get to that point on our circle. So I wanted to ask you all if we could come up with a different way to write these functions by only using the other functions. So it's kind of a weird question. Give you a second to ponder it. But instead of saying that sine using our Sohcahtoa for our big three, sine, cosine, and tangent, and their ratios, the opposite over hypotenuse. For cosine, adjacent over hypotenuse, and tangent, opposite over adjacent. When we are on our x and y axis, to get to any point in any quadrant, we said we could march over some x, up some y, or we could just get directly to that point, x comma y. And we said that we could rotate this around to any of these points and form a circle. So that angle to get us to one of those quadrants would be some radius on this circle. So we use the letters x, y, and r to list, instead of just opposite and hypotenuse, adjacent, hypotenuse, and opposite over adjacent, we said sine would be the y over r, cosine, x over r, and tangent, y over x. And those are what I like to call the big three, because if you know those, then you should know these. They're just called the what of the big three. Good. Somebody put in the chat, reciprocal. That is the proper term. Very good. Excellent. So if this is y over r, then this would be r over y. X over r over x, y over x, x over y. But what we're trying to do now is change it in this last section of chapter 1 to only write these trig functions in terms of other trig functions. So obviously I know that this is related to this by just flipping it the reciprocal. And remember, if it says reciprocal, then that means that we should know that this sine over 1 would be equivalent to 1 over its reciprocal. And let me show you what I mean by that, and I won't do this for everyone, but we know that this is equal to the y over r. And we know that cosecant was the reciprocal of that, so it's r over y. And as you guys know, we don't like fractions within fractions, but we also know that we can multiply by a fancy 1 and get rid of all of those things, because we know r over r and y over y are all 1s. So that then gives me just y over r. And so you can see for sure that they are equivalent. Okay? So that's my proof that I don't want to do another time and another time and another time for all of these. Okay, but hopefully you'll take my word on it, that if we know that sine, its reciprocal function is cosecant, then we know that sine is going to be equivalent to 1 over its reciprocal. In other words, we're basically taking the reciprocal of the reciprocal to get it to be back to the original. Hopefully that makes sense. A little weird, but I wanted to at least prove it once. If you guys want to see another, I can do it for cosine or tangent or whichever you would like. But if we know sine is equal to 1 over cosecant, then what should we know cosecant is equivalent to? Flip that and you get cosecant over 1, which means we'd have to flip that, which would give us 1 over sine in order to keep it equivalent. It's like saying 2 over 1 is equal to 4 over 2. That's definitely a true statement. But if I flip this side, I'd get 1/2, which means I'd have to flip this side to get 2/4. And that's basically what we're doing with this and this, now that we just proved that these are equivalent. So cosecant is equivalent to 1 over sine. So if we ever see 1 over sine, rather than keeping it as a nasty old fraction, we could just write it as cosecant. Okay, do you guys want to see another proof of why it is, or do you guys want to just tell me what cosine would be? I'm good either way.
For cosine, it would be 1 over secant, right?
Very good. Excellent. Which means what is secant if we know that?
1 over cosine.
Very good. Just flip them. Do the reciprocal. So that would be 1 over cosine of the angle. Whatever the angle is of this one has to be the same as that. We're calling it theta. How about tangent, cotangent?
For tangent, 1 over cotangent, and then for the other one, 1 over tangent.
Very good, Samara. So thankful for the participation and you showing up. Otherwise, it'd be me talking to a bunch of black screens. Thank you. So since these are just the reciprocals of one another, when we put this over 1 and that over 1, guess what we're going to call these? We're going to call them the reciprocal identities. Okay, and again, identity meaning that it's identical. So whether you have 1 over cosecant of some angle theta or sine theta, you can write this as that or this as that. Okay, so I will tell you right now, most of the time, what you will use these for are these. Okay, we will have the sines, cosines, and tangents most often. And instead of having them as big, nasty fractions, we will prefer it to just be a single trig function without the fraction part. Okay, you will not most of the time have it as this. Doesn't mean you can't, but you just need to know that this would be equivalent to that. All right, identical. That's the symbol we use for it. We just call them identities. All right, pretty simple. Now we're going to move on to something that we also spoke about a little bit last week, but I wanted to dig it in a little bit deeper so that you guys make sure that you don't make these little mistakes. And those are the rules for our sines. for all 6 trig functions. Again, we'll focus on the big 3 and then talk about what would happen if we just flipped them. Still be positive, still be negative. Okay. So which would be positive and which would be negative? Well, I drew our 4 quadrants. Now, if you don't know why this is the first and this is the second, the third, and the fourth, you need to watch my videos. Okay. But think about what we started with. And that was just a single number line. This right here. And remember, this 0 split the positives from the negatives. Well, then when we added the other axis, we call it the y-axis, which is just another number line where the 0 splits the positives up and negatives down. Well, where are we going to start? Because this splits it into 4 different parts, we had to choose to start somewhere. And of course, we decided to start where? We started counting positive in the x direction, and then of course positive in the y direction. So quadrant 1 is going to be where we're positive. Well, then we had a choice. Are we going to go from here to there or here to there? Do we want to start rotating downwards or do we want to start rotating up and around? And of course, we said, well, then that means one of these things are going to have to be negative. Are we going negative in the x or are we going to go negative in the y? And because x was the first axis, the number line, we said, you know what? Let's change that first. So that's exactly what we did. We said, all right, well, let's change that to a negative and keep that positive. So now we're going negative and positive. And that's what we call quadrant 2. And of course, then we had a choice. Well, we only have 2 other quadrants left, but we wanted to keep the flow from 1 to 2. So this is definitely 3. And then that is definitely 4. And remember, all of these things change as far as the x and the y to get there. How would they change in quadrant 3? We'd have to go left, which is negative on the x-axis, and then down, which is negative in the y. So you can see all the ordered pairs in this quadrant are all going to be positive x, positive y. All of them in this, negative x, positive y. Negative, negative, and here, positive, negative. So for my last quadrant 4, we will have a positive x, negative y. So if you remember, all of our trig functions, sine, cosine, tangent, and we'll worry about the other 3 to get to our total of 6 once we figured these out, our big 3. What do we say the sine of any angle is always going to be? The what over the what if we're on our xy axis? Anyone? Sorry for those of you that are watching this back. Hopefully you're answering. Y over R. Then cosine. X over R. Oh, sorry. Somebody's going to answer. Go ahead, Charles.
Oh, there you go. I was just going to say x over r like you just said right now.
Perfect. Beautiful. And then how about tangent?
Was it this one r over y?
Close. R over Y would be the reciprocal function of
Oh,
sine.
yeah. Sorry.
That one is y over the x. Now, remember, if we're at any point, this one, which would be some positive x and positive y, or this one, which is some negative x, positive y, what would the r be anywhere on here? What would my radius length be at any one of these points? Well, it's kind of a trick question because we don't know, but we do know it's going to be some length, some distance from our center out to a point on our circle, which means if we're dealing with distance, remember one of the things we reviewed at the very beginning, absolute value, talked about that a little bit, right? And that would be a distance, which means our r is always going to be positive. So when we're looking at sine, we're really only looking at the y value because this is always going to be positive. So to see if it's positive or negative in which of the four quadrants, we really only need to focus on the y value for sine. And we know that this line right here, the x-axis, separates the y values that are positive from the y values that are negative. So what does that mean? Sine will always be in quadrants 1 and 2? Positive. And therefore, what would sine always be in quadrants 3 and 4? Negative.
Negative.
Very good, Samara. So we're really focusing on that. Now, here's the cool part. We know that everything in quadrant 1 is positive. That's the x, that's the y, and remember, r is always a positive distance. So what we are going to say for all of these is that in quadrant 1, everything's positive, all of them. Now, what about in quadrant 2? Of our big three, sine, cosine, and tangent, what's the only one that is going to be positive there?
Sine.
Good, because remember, both cosine and tangent have an x involved. And notice in quadrant 2, the x is negative. So we're going to put a big capital S to represent sine is positive there, which means what are the others?
Negative.
Very good. How about quadrant 3? Quadrant 3 is a little tricky because my y is negative and the x is negative. But notice tangent has both of those, doesn't it? It has the x and the y. And if we have a negative and a negative, what does that always yield? So therefore, tangent is the only one that's positive in quadrant 3. So you can probably guess what quadrant 4 is. We got sine, we got tangent, now we got cosine. And again, why? Because r is always positive and x is positive in this quadrant. Because the y-axis splits the positives from the negatives. So cosine in the positive x, sine in the positive y. Tangent, where both x's are and y, are the same in either quadrant, 1 or 3. Now, what about the other 3? Well, remember the other 3, cosecant, secant, and cotangent, are just what compared to these? We call them the reciprocal, which means Are the values going to change? Well, yeah, because it's going to change from a y to an r being flipped. For example, a 2 and a 1, if you flip those, we're going to get, instead of a 1/2, a 2, which is much larger. Okay? But if it was a -1/2, well, then this would still be a 2/-1. Notice the sign is not going to change. So that's why we only focus on the big three. Because if we know what sine is, cosecant's going to be the same. Sine, not value. Cosine, same sign, reciprocal value. Okay? So again, there's why I wanted to explain it to you rather than just give it to you in that form. But again, we're just going to focus on all students' text in class, or all students take calculus. Okay, those are the monikers that I want you to remember. And all this helps us to do is what? To see whether your trig function values will come out positive or negative. Okay? So, last thing I want to do is derive a few more of these identities or identical formats to use throughout the course. And again, throughout, it's going to be a lot. Today's super important for us. Okay? So if I was to get to this point, and again, I'm just going to put it in quadrant one to keep it simple. All right, then I know I would get to that point by either rotating some angle theta and marching out some radius length r, or I could go over that x, up that y, and create my right triangle. Now, what was one thing that we said that we could use if we are given a right triangle? It was last week, we talked about it. It rhymes with Pythagorean. It's called the Pythagorean Theorem. Okay, just trying to give you a little hint there. So if I have x squared plus y squared, remember the most important in the Pythagorean is the hypotenuse, the longest side. Well, then if I want to introduce my trig functions, that means I need any of these ratios, which means we need fractions. And so what we're going to do with this is actually just, because it's an equation, I can do whatever I want. I'm going to divide everything by, I don't know, what do you guys think? What would be a good thing to divide everything by? How about by the r squared? If I got all of this equals to 1, that'd be pretty nice. So again, as long as I do it to everything, okay, as long as I do it to everything, it will still be equal, an equation. And now I have this whole thing equal to 1. But I'm going to be a little creative here. And instead of just keeping x squared over r squared, I'm going to write it as x over r quantity squared. I can do that because that's still just each of these things having to be squared. And I'm going to do the same thing here. And hopefully you guys now recognize I got some stuff that we should know, namely an x over r and y over r, which means I can replace the y over r and the x over r with what? Now remember, you need an angle with your trig function, otherwise it's a sin. But remember, sine was the opposite over hypotenuse, the y over the r. So I can replace that with sine. And then the x over r was the adjacent over hypotenuse, which is the x over r. But I don't really like the form of this. I do like that it's equal to 1. I just don't like writing the big parentheses. And do I need them? Is that okay if I just took those away? Well, unfortunately not, because now it's saying to square the angle and then take the cosine of that new angle. We had the whole thing being squared. So we got a little creative. Mathematicians, we're kind of lazy. We'd rather just use symbols and write down words, and the less symbols that we can use, the better. And we said, we're just going to write the squared on the thing that we're actually squaring, not the thing that we're not, which would be the angle. So when we write this, we're going to write it as sine squared of the angle plus cosine squared of the angle, all equals 1. And because we just proved that this is equal to 1 by doing a little bit of manipulating to our equation, because we got it from the Pythagorean theorem, we're going to call this a Pythagorean identity. Now, if you notice, it says identities, plural. This is the only one that you have to memorize. But where are we going to get the others? Are we going to come up here and divide by something else, like an x squared or a y squared to everything? Not really. What we are going to do is get the other 4 trig functions involved, not just sine and cosine. Okay, but that's going to require some of the stuff that we already just got done talking about. So this is the one that I want you to memorize. You need to memorize this, and you need to memorize it quickly. Okay, this is the one. No pun intended. But what we're going to do to that one is just manipulate it. So if I had sine squared plus cosine squared theta equals 1, what can I do to an equation? I can do anything I want. And if I want to get rid of that sign, what would I have to divide by to get rid of it?
Divide by itself.
Very good. And if I do it to that, to keep it equal, I'd have to do it to everything. And Samara, why did you say that? Well, anytime we divide something by itself, what happens? All of that cancels out. And now we have 1 plus something equals something. We just want these somethings to not look so nasty. And do we know what 1 over sine squared theta is?
It's cosecant.
Very good. We just went over 1 over sine is equivalent to cosecant. That's the one I actually derived for you. Okay. And because it's squared, then that means we have 1 over sine and times another 1 over sine, which means we're just going to have cosecant squared. Now, this is going to be a segue into the next thing that we're going to talk about. So we're going to do it simultaneously. But what is cosine over sine? And we'll get to the squared part in a minute. But what is a cosine over a sine? We'll worry about them being squared in a minute. Well, what do you know cosine of an angle is? Always. What is cosine theta always equal to? I'm going to submit these home. I'm going to just keep saying them over and over and over again. Hopefully you guys will start participating and say something. It's x over r. How about sine then?
Y over R.
Well,
Very good, both of you. Y over r. And again, we don't like fractions within our big fraction. So how do we get rid of the denominator so that we could just focus on one thing up top?
Multiply both by R.
Good. R would just get rid of the bottom though. I want to get rid of all of this.
So then multiply it by Y over R.
R over Y. It's called the reciprocal. Very good, Samara. R over Y instead of Y over R because R over R cancels and Y over Y cancels to be a 1. Now, when I divide by 1, we can forget about it and just concentrate on the top. And notice what else is going to cancel out for us. The R's, which means the only thing that's left on top and bottom when we multiply across is the X over Y. And does anybody remember what X over Y was equivalent to?
Cotangent.
Very good. Excellent. So we know since this is equal to this, which is equal to that, then that means these two things are equal. And that makes me happy. Okay. So we can say that this whole thing is equal to cotangent of theta. So going back to what we originally started this journey as, cosine over sine, just because they're squared means that we will have cotangent squared of that same angle. And here is a new version. That again came from the Pythagorean identity. Now, if you want this equal to 1 as well, just like this, all you'd have to do is manipulate it by moving that over. So we can rewrite this as cosecant squared minus cotangent squared is equal to 1. But we got sine and cosine. We got cosecant, cotangent. We're missing tangent and secant. So guess what we're going to do again to that equation?
We're going to divide it by the other one.
Good. And what is
by
the other one?
cosine.
Very good. I will now manipulate by dividing all by cosine squared theta. Again, the reason I have to do it to all is to keep it equal. And definitely know that that becomes a 1. We definitely should know what 1 over cosine is by now.
Secant.
At least I know Samara does. Thank you. And because it's squared, remember, squared. And then what would you guess that sine over cosine is? Since we now know that cosine over sine is equal to cotangent. Notice this is just the what of that.
The reciprocal.
And since cotangent is the reciprocal of what?
8. So for cotangent, it's, yeah, 1 over tan, right? So we just put that one down.
Very good. Now, again, let me show you why, Samara. I want to make sure that everyone's clear that this is tangent. Again, because they're squared, it'll stay squared. And then we'll go back to that. Let's take what we had, which was sine over cosine this time. And again, what do we know that sine is always equivalent to? The what over the what?
The y over r,
And what is the cosine always equivalent to?
x over r.
And just like we did last time, let's multiply by that fancy one. Told you guys, super important concept in this class and in all math of the reciprocal of the denominator. Because then the x's become a 1 and the r's become a 1 whenever we divide something by itself. And since this is also multiplying, the r's will cancel, and the only thing we're left with is a y over x, which we said is equivalent to tangent. And since that's equivalent to this, which is equivalent to that, which is equivalent to that, then we know that these are equivalent. Oh, and by the way, those are therefore what we are going to call the quotient identities. Because these things are identical. And rather than having two trig functions as a fraction divided, we can write it as 1. Much better. Okay? So the quotient identities I will put over here. We know that sine over cosine is now the same as writing what?
Tangent.
The y over the x. Very good. And if I flipped both sides of those things, I took tangent and flipped it, which would be 1 over tangent, which we know is equivalent to what?
Cotangent.
Very good. Then I'd have to flip this side, which would be cosine over sine of that angle. So I know that this is equivalent to that. Or I just proved it to you here. So cosine over sine. When you have the cosine on top, it's going to be cotangent. And then we got our 3 Pythagorean identities. The main one, sine squared plus cosine squared of the same angle will always give you a 1. As long as these angles are the same, they're squared and added together in any order, it's equal to 1, which means you can replace all of this with a 1. And that'd be really nice. That's a great identity. Or if you have cosecant of an angle. Let me fix that. That's ugly. Cosecant of an angle minus cotangent of that same angle being squared, then that's also equal to 1. Or over here, if I wanted to get it set equal to 1, I would have to subtract the tangent to both sides, and I'd get secant squared minus tangent squared is also equal to 1. Okay, so these are nice to know. This is necessary to know. Okay, you have to have that one memorized. Why do I only really care that you have this one memorized? Because you can get the other two by simply just dividing everything by a sine squared or a cosine squared. And that will give you the others. Okay, will it be faster to just have these memorized than having to do this and that to these to get those? Absolutely. So the more you memorize, the faster and easier things will be for you. Okay, so that is it, my friends, for this first section of today. Make sure that you start memorizing as much of this as possible. Right, there they are in their generic forms. We call them the quotient identities because that's what they have, is a quotient, a division, a fraction. And then the Pythagorean, because it came from the Pythagorean Theorem. Manipulated. So there they are for your notes, a little bit cleaner. Otherwise, I'll see you at the next section in the next video. All right, welcome back. Another video here of 2.1. Now, this is the beginning of chapter 2, which, as I mentioned before, one of the most important chapters of this entire class. The more you memorize, the easier this stuff will be. So if it sounds repetitive, it's because I want to repeat over and over and over so that it ingrains in your brain some of these main things that we're going to be talking about, utilizing over and over and over again. So without further ado, let's do chapter 2. 2.1, trig functions of, we're going to just focus on acute angles. Now remember, that's one of those mini definitions that we talked about in that first chapter. Acute, meaning between 0 and 90. So I'm just going to focus on quadrant 1. Now we haven't officially defined our functions using the most commonly way that we will see and use these trig functions, which is going to be on our x and y axes, not just some triangle floating out in space. Okay, but again, to get there, we would have to march over some x and up some y. Okay, and once we've done that, we know that we formed a 90-degree angle because the x-axis and y-axis are perpendicular to one another. So if we go left to right and then up or down, then we know we form that 90. And as we mentioned, if we rotated around more than just that much to get to this point, then we would create, if we go more and more and more all the way around 360 degrees, we create a circle. So we said that this would be called R. And the angle opening would be that Greek letter theta. So let's see if you guys can say exactly what we said these would be. And again, I'm going to start with the big 3, and then we'll talk about their, what do we call these?
Reciprocals.
Very good, Luis. Reciprocal functions. So what is sine according to this triangle and that angle? What ratio?
Y over R.
Excellent. Now remember we said the Sohcahtoa can play, but that's more geometry. We're getting into trig. We're going to be dealing with the x and the y axis more often than not. Not always, but more often than not. So it's better to memorize it like this than the opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent. So sine, y over r. Cosine,
X over R.
and tangent.
Y over X.
Excellent. Very good, Luis. And that means if we know that, we should know these because they're just the what of these,
The reciprocal.
which is why we called them the reciprocal functions. Very good. And therefore, all you have to know is which one pertains to what. And remember, for the sine and the cosine, you gotta not keep the s's and the c's the same. It's going to be 1s to 1c or 1c to 1s. In order to flip it, you got to switch it. So the sine and the cosecant, which would therefore be r over y. The cosine and the secant, r over x. And tangent and cotangent, the easiest pairing, x over y. All right, is this anything new?
Nope.
Nope, I agree. But again, you need to memorize especially these three. Because if you know those three, then these three are easy. Okay, so now that we've officially done that, I'm going to continue to ask you what these are, and then we'll go from there in order how to use them in different ways. And that starts right now. Okay, not always will we get nice values out, and I don't like calculators. You know why? Calculators are never wrong, but there are user errors. And so there's this kind of feeling that students get that as long as I can use a calculator, I'm good. Well, you have to still know what to calculate correctly and input correctly in order to get out the value that you need. So the cool thing is I don't really require calculators very often, if at all. I'd rather you guys, instead of just punching in calculator work and giving out some nasty, long, weird decimal answer that really makes no sense, I'd rather you guys give me the exact answers than those approximates. And so what we're going to talk about is the ones that do actually work nicely with all of our trig functions. And I put so nice, in fact, that we can do it without using a calculator. And does anybody know what those special values are? Or want to guess? On that circle, no matter what point you choose, if you land on one of your four quadrants, that's really nice. Because if I'm here, and let's say that the circle's radius is 1, a length of 1, then I know that this distance to get there would be an x of 1, and I'd be up and down none. And remember what we just defined all these using? What three letters? So if we know the x, the y, and the r, then we can give any of the 6. So if we land on one of our quadrants, remember we called these quadrantal angles because of that, which are just multiples of what value? Right? 90 degrees, 180, add another 90, 270, 360, and we started at 0. Remember, those are the 5 quadrantal angles. And technically, you're looking at 1 point here, but we use 0 and 360 to both start and end in that one full circle. So definitely the quadrantal angles. But what about if we don't land directly on one of our 4 quadrants? Then that means we're either in quadrant 1, 2, 3, or 1 before 5, 4. And I don't know if you guys remember from geometry, they were called special right triangles because they too were special. All right, just like all of you. You're special because you're in my class. All right. And you're going to learn all of these things. And again, if you can what? Will it make it a whole lot faster?
If we memorize?
Exactly. Then it will make all of the trig that much faster when we get away from just these special right triangles of geometry. Okay, so I'm actually going to derive these with you just to make sure that you understand why these are what they are, and then we'll move it over to the trig. Okay, so very quickly, what makes a 45, 45, 90 special? Now, remember, we said that the sum of all of the angles have to add up to be 180. So you can see my 90 and my other two add up to be 90. There's my 180. But if this opening right here is a 45-degree angle, and this opening is created by these two sides, then I know that this is some length. But if this is also a 45, which is created by this same side as this one, and now this, which was what this one made, what do you think has to be true about this opening that created this side and the same size opening that creates this side? What do they have to be?
Are they congruent?
Very good, Luis. I love the terminology that you use. They have to be the same size. They're definitely not the same because this is the height and this is the base of my triangle, but they are definitely the same size. How big do you think they are? Or does it matter? Well, here's the cool thing. I don't know that length. I mean, I could get out a ruler and measure exactly how many inches or whatever, but it doesn't matter for what we're trying to accomplish. So we're going to say that this length is A. And because they're both 45 degrees, we know that the angles are going to create the same size lengths as well. Which means, if you guys remember, if we know 2 out of the 3 sides of a right triangle, what can we do to find that third side length?
The Pythagorean Theorem?
Very good, smart. The Pythagorean Theorem, which, what did I tell you? Of the 3 sides, what's the most important?
Hypotenuse.
Very good. So I'm going to take the 2 legs, square them, add them together, and I want to find what that third, that hypotenuse, actually is equal to. So since we know that this is A and this is A, what happens when we square an A? We get A squared. But what happens when I take an A squared and I add another A squared? Do I have A to the 4th? No, remember, when we add things, as long as they are alike, we will have more of those things. We subtract, we have less. So the only thing that's going to change is the quantity. We call it the coefficient, how many A squareds we have. And since I have 1 here and 1 here, I then have a total of 2 A squareds. And since that's equal to the unknown side, the hypotenuse squared, what do we have to do to find that unknown? To undo the squaring, we'd have to take the square root. Now remember, when you take the square root of something, you need to give me both the positive and the negative case. Because what this is looking for is what squared gives me that. And that's why we're trying to undo it by taking the square root. And when you square something, whether it's positive or negative, it will come out to that positive value. So that's why whenever you take the square root, you need to include the plus or the minus. Now, do I know how to take the square root of 2 or A squared? Yes, I know the square root of something squared is just going to undo one another like we did there. So I'll get to take the square root of that and rewrite it as a root 2. Now, because we're dealing with a side length and we're not on the X and Y axis, there's no reason to have the negative there. So we know the answer to this is simply just a root 2. Do you guys remember that at all? In a 45, 45, 90, as long as you know any one of your sides and you can solve for that A, then you know the values. If A's are all 1, then this is a side length of 1, 1, and 1 root 2. If they're all a length of 5, this would be 5, 5, and this would be 5 root 2. It's very simple. That's what makes these special. You only need to know one side length and you can know all 3 based off of that. So let's get to the next and last special right triangle we're going to talk about, which is a 30, 60, 90. Now you might be looking at that and you're like, okay, 45, 45, 90. I saw it. You wrote it all out. But now you're looking at this, and what kind of triangle is that?
Equilateral.
Very good, Luis. If this is 60, this is 60, and this is 60, and that opening creates this side, and that opening creates this side, and even this one, then what do we know? Since all of these are the same, all their sides have to be the same. So guys, how long is this side, that side, and that side? What do you think? Yeah, me neither. I don't know. So we could call it A to represent any length again, but for the purposes of making this simpler, I'm actually going to call them all a length of 2A. You'll see why in a minute. Because what we're trying to form is not a equilateral, equiangular triangle. We're trying to make a 30, 60, 90. So take any one of these angles. I'm going to take the one up top, and I'm going to cut it in half by dropping this perpendicular. So by drawing this perpendicular here, that is going to then take and split this into 2 equal parts, which means since these are both 30, it's going to create these into equal parts, meaning it's going to cut this whole length we called 2A into a length of A and A. So do you see why I'm calling it 2A rather than just A? Otherwise, that would be half and half. Ugh, no fractions. Everybody good there?
Yes.
Well, then I actually know how many sides of one of these, pick any one, 30, 60, 90 triangles, whether it be this left half or the right half. There's your 30, 60, 90. And do you see that I know 2 of the sides? Well, then let's find the third, which is actually the height of this, not the hypotenuse. And remember, if we have a right triangle and we know, quote unquote, we know 2 out of the 3 sides, should we be able to find the third?
Yes.
Careful. Yes. How?
Pythagorean theorem?
Good, but what did I tell you is the most important piece in the Pythagorean?
The hypotenuse?
That's the one that's by itself. So our unknown value this time is going to be one of our legs. So now I want to take this equation and solve for my unknown value again. I'm not calling it x, I'm leaving it as a question mark because we already have variables in there. I don't want you guys to get too confused. So square that, and square that. What do you get? My a squared gives me a squared. My question mark squared gives me question mark squared. Careful, what does 2a when you square it give you?
4a
A.
squared.
Oh yeah.
And that's what a lot of people will not do. They will just square the a, like the 2's not inside being squared as well. You got to square the whole thing. Very good, Charles. So that gives me 4a squared. What's my next step?
Oh, you get the a squares by itself, right?
Do
Like
we
minus.
want to solve what the a squared is? No, we want to solve for the question mark squared. So I think you followed it up with, I heard you start saying it. We want to subtract the a squared over.
Yeah.
Careful. I know when I take an a squared and I subtract an a squared, I have no a squared. So I just put nothing or just cancel it out. What's left is my question mark squared, and it's equal to what over here?
4.
And that's what a lot of people make the mistake of. Samara, remember when you add or subtract, the only thing that's going to change is how many you have. What do I have here? 4 what?
4a squared.
What do I have here?
Minus a squared.
So when you say 4, you just canceled out what you saw was the same, right?
So
We
it'd
have
be, yeah,
4 of these and we're subtracting 1 of those, which means what do we have?
3a squared.
Yes, ma'am. A lot of people make that mistake. Remember, when you're adding, you're going to have more of that thing. Subtracting, you're going to have less of that thing. But that thing is not going to change or go away. All right? Here it did because we had 1 and we subtracted 1. So now we got none. But it doesn't magically just get rid of the a squareds. You got to know how many a squareds you have. And now that we almost got the part that we wanted to know by itself, what do we have to do to get it by itself? Again, we got to take the square root, which means we got to give them both cases. And when we take the square root of something squared, we get it out, which is why we did what we did. And because we have that here only, what's still going to be under that root? My 3. And what am I going to be able to pull out and take the square root of? That a. And because we're still dealing with a length or side of a triangle, we don't need the negative. We're not on the x or y axis. And therefore, we just found that a right triangle with a 30-degree, 60-degree, and 90-degree angle opposite the 30, the smallest angle, gives me the smallest side. It will be a length of a. Opposite the 90, which is the biggest angle, gives me therefore the biggest side. It's twice as big as that 30, that small side. And since this is 1a and this is 2a, and this was the 30 and the 90, we know that 60 has to be somewhere in between 1a and 2a, and we actually found it's exactly how much bigger? root 3 times our a. 1a, 2a, root 3 times is a. We usually just put the root 3 in the back because we don't want the a to look like it's underneath the root. So we usually put it in front. Which again means as long as we know any one of these three sides, we can solve for a and use it to say what all three side lengths are. That's again what makes these special. So make sure that you have this written down and this written down. Somewhere, highlight it in your notes. These are things that we're going to use a lot. And I mean a lot in this class. Namely, the 45, the 30, and the 60. We already know the 90 is part of our quadrantal angles. Right? So then help me out. Let's take those things and find these values. I'll draw them again for you real quick. Or let's do it together. What is the 45, 45, 90 values? And then what are the 30, 60, 90? Let's start with the easiest one, 45, 45, 90. What do you know is opposite the 45s?
Is it A?
It is. It could be any length, but we know that they are the same because the angles are the same. What do we call this side length opposite the 90?
The hypotenuse,
Why do we give it that special name, Samar?
because it's the most important one.
Why? What will it always be in your triangle?
It'll be the biggest side.
Very good. That's why we give it a special name. So since this is 1a and this is 1a, we know that this has to be bigger than 1 times our a. And what do we just find it was? How much bigger?
A square root 2.
Very good, Luis. It's root 2 times as big. How can you remember 1 has the root 2 in it and 1 has the root 3 in it? Root 2 is with the one that has the two angles that are the same. Root 3 has the 30 in it. The 3. So how about the 30, 60, 90? Opposite the smallest angle has to be my smallest side. Therefore, we're going to start and say it's how big?
A.
It could be any size. That's good. Now let's go to the biggest angle and therefore the biggest side. How much bigger was it than the smallest?
Twice.
And since this is 1a and this is 2a, smallest side, biggest side, we know the one in between it has to be between 1 and 2. And we went and discovered it was root 3. Now that we have these, can you now start evaluating? And again, I'm just doing the big three, sine, cosine, and tangent for these important angles, the 30, the 45, and the 60. Let's do it together. Let's start with the sine of 30. Here's my angle 30. What do we know? Sine is always the what over the what?
Y over R.
Good, but the y, x, and r stuff only work when we're on our x and y axis, which we are definitely not, right? So that's where the Sohcahtoa also comes in handy. Again, most of the time will be on our axes, but sine we know is the opposite over what?
Hypotenuse.
And because this is a 1a and this is a 2a, what can we do to that to simplify? We can cancel out our a's, and what's left?
One half.
Which means the sine of 30, no matter how big, that's what a represented, was anything, no matter how big my triangle is, what will the sine of 30 always yield?
Half of the value.
Beautiful. Then I'm going to memorize it. Because it doesn't matter how big my circle is. If I have a 30-degree angle, no matter what these side lengths are, the opposite and the hypotenuse, they'll always be this ratio, which means it will always, no matter what those lengths are, simplify to be 1/2. How about the cosine of 30 then? What would it be? Well, it would be the adjacent over hypotenuse, not the opposite this time. So a root 3 over a 2a, and again, since these are multiplying, I can cancel the a's. I'm telling you guys, that's why these are special. The lengths of them with all those a's doesn't really matter. Because what's going to happen here again? The a's cancel out, and what are we left with? So what is the cosine of 30 degrees in any triangle going to give you?
Square root of 3 over 2.
When?
Over any of the values.
Always. For any size triangle. If I blew it up to be this big, and the 30 was down here, the 60 was here, and the 90 was there, or these were reversed, the cosine of 30 would always give you root 3 over 2. The sine of 30 will always give you 1/2 for that ratio of opposite over hypotenuse or adjacent over hypotenuse. And therefore, what would the tangent of 30 be? Opposite over adjacent. And again, what can happen?
The a's cancel out.
Now, when you say cancel, remember that means simplify to be a 1, right? Because we have to have something on top. It can't just disappear. So we have 1 over root 3. Does anybody recognize that? Do you remember that very first group quiz that I gave you all, that big packet of prerequisite stuff? And I was trying to emphasize how much we use the multiplying by 1, the solving equations, factoring all those little things that we've talked about and dealt with in the past. This was like number 5 or 6. I don't know if you guys remember it. It was just this. And I asked you to simplify. Remember how we multiplied by the square root of 3 over the square root of 3? To get the square root of 3 over the square root of 9, which is the square root of 3 over 3. Guys good with that?
Yeah.
When is the sine of 30 going to equal 1/2?
Always.
The cosine of 30, root 3 over 2.
Always,
The tangent of 30, root 3 over 3.
always.
So, math family, what's 3 times 8?
24.
How'd you know that so quick, Samara? Is
I
it always
memorized it.
24?
Yeah.
So that's why you took the time to memorize it. I'm going to give you guys college level multiplication tables for you guys to memorize. But I'm not going to sit here and derive them all with you again. Okay, let's just do them real quick. Everybody okay with that?
Yeah.
Yeah.
So let's do the sine, cosine, and tangent of 45, which means now we're in this triangle. And does it matter which 45 we're looking at? No. Because if I'm doing sine, I'm looking at the opposite over hypotenuse. Or if I did this sine, it would be opposite over same thing. So I get a over a root 2. How about the cosine of 45? That would also be a over a root 2. But as always in math, we want to simplify. So cancel, like we talked about, the a's. Because we're multiplying, we can do that. We know anything divided by itself is 1. And when we multiply by 1, we get the same value. But we don't like the fact that this is 1 over root 2. So we got to multiply by a fancy 1 again. And what's going to happen? What are we going to multiply by?
Times the square root of 2 over 1.
Not over 1. Remember, it has to be a 1. And if you
Right,
multiply
over
by
itself.
root 2 over 1, now you're making it that much bigger. Does that make sense?
Yeah.
Got to be that fancy 1 I told you we're going to use very, very often, and it's super important. So what do we end up getting? On top, root 2. On bottom, root 4, which is just 2. And that's why we did it. Since this is the same, I know I'm going to get the same value. So that's kind of cool. Sine and cosine actually get the same value. But hear me out. I don't want to have to do all this multiplying by 1 and rationalizing the denominator for tangent as well. I know that the tangent of 45 is actually just sine over cosine, isn't it? Didn't we review that in the last section? That sine of an angle over cosine of that same angle is equal to tangent. So since I know both of these values, can I just put one over the other?
Yeah.
And what is anything divided by itself?
1.
Beautiful. Now, again, if you wanted to go off and do it on the side real quick, you could go to tangent and do the opposite over the adjacent, and you get a over a. Pretty easy to see. It's 1. Okay, last one here. Let's do the 60-degree angles. Now we're up here. And for sine, it's going to be the opposite over adjacent. Or excuse me, hypotenuse. Cosine, adjacent to the 60, should be a over the hypotenuse. And toa for tangent, opposite over the adjacent. Simplify all of those, what do you get? Root 3 over 2, 1/2, and root 3. And does anybody recognize some of those values? This super important for us to start memorizing And you guys are going to learn right now why we actually call some of these things what we do. Right? You guys know that sine. And then there was cosine. But you never knew why it was called cosine. Why is it called cosine? Because they are what are called cofunctions. If you notice that the sine of 60 and the cosine of 30 gave you the same ratio or value out. The sine of 30 and the cosine of 60 gave you that same value out, 1/2. So what's the relationship between sine and cosine? They are what are called complementary functions. They just smashed these words together and called them cofunctions. Why cofunctions? Look at the angles of sine and cosine. And if they are complements, remember complementary was when they added up to be what?
90.
Then notice their ratios are the same. So if you have memorized the sine of 30 is 1/2, then you should also have memorized that what? Cosine of 60 is 1/2. And if you have memorized that the cosine of 30 is √3/2, then you should also know that the sine of 60 is √3/2. And obviously the sine and cosine of 45 are the same. We saw that. But what about tangent? What do you think its cofunction is? No idea? It's cotangent. So sine and cosine, that's why they are named what they are. That's why they are defined what they are. They are complementary functions. So I know that this is equivalent to that. I know that this is equivalent to that. And of course, these are definitely the same. Complementary functions, which means tangent and cotangent are also complementary functions, which means what else would be equal to √3/3 besides tangent of 30?
The cotangent of 60.
Very good. What else would be equal to 1?
Cotangent 1.
Cotangent of 45, right? You're giving me the angles for the outputs to be the same. And if I know the tangent of 60 is √3, then the cotangent of what would also be equal to √3?
30.
60 degrees would be √3. Oh, 30.
Right? Notice all of these add up to be what?
90 degrees.
Because they are cofunctions, complementary functions. Okay? Now there's two that we haven't talked about, and that is obviously which two?
Secant and cosecant.
Wait, what did you say, Luis? Secant and what?
Cosecant?
Why do we call it cosecant? It's the complement to secant. And how would we get all of those values? Well, if we know sines and cosines, flip them all. That's it. Okay. Pretty simple stuff, but it's a lot. There's a lot to memorize and take in. All right. So wanted to make sure that you guys understood what we just talked about a little bit more clear. And here's the way that we're going to explain it. If you know the sine of any angle, call it A, then what do you know it's equivalent to? The complement of it, which means if we know the sine of, say, 40 degrees, then we would know the cosine of what? 90 minus that 40, which would be 50 degrees. So again, let's say that this angle was 40 degrees. Then if we do 90 minus 40, that would give us the 50 degrees. That adds up. And notice which ones pertain to what? Sine and what?
Cosine.
Very good. Secant and what?
Cosecant.
Tangent and what?
Cotangent.
That's why they are named what they are. Cosine, cosecant, cotangent, because they are cofunctions, which means they're complementary. And if they are complementary for those cofunctions, then we know their values will be equal. All right. So here's the last thing for today I wanted to show you is how that you can memorize these a little bit quicker is by building this. So you know we start at 0, we go to 90, right? We want to make that right angle to get in that first quadrant. Well, then if we had that, we want to look at the 30, the 45, and the 60 as well. And so we want to memorize these. Okay, so check it out. Sine, cosine, and tangent, the big three in order. We usually start with sine because this is cosine, all right? And then 0 to 90 and all those special angles that we talked about. So this is really cool, really simple. Make sure that you guys follow along as I do this so that you understand how I did it. Okay, it's pretty simple. We're just going to start at 0 and then go up to get to our quadrant, the fourth thing, the 90. And because cosine is the complement to that, we're just going to do it in the reverse order. So instead of left to right, we'll go right to left. And we will say 0, 1, 2, 3, and 4. Because we knew that they were complementary functions, these things will complement each other and all add up to be 4. And by memorizing this, it's going to cut your time in half. So all you got to do is take every single one of these values and get the ratio, cut it in half. But don't forget, unfortunately, we're dealing with these things and they have those right triangles. Pythagorean theorem is how we got a lot of these values. And therefore, we're going to have square roots on top of every single one of these. Now, of course, that's how you can do it, but we want to simplify and then start memorizing these. So let's say what each and every one of these would simplify to be. What is the square root of 0?
0.
Divided by 2.
0.
That means we start with the 0. What's the square root of 1?
1.
Divided by 2.
0.5.
I don't like 0.5. Give me ratios. I want to see my y and my r, and you'll see y as we progress through. All right. How about the square root of 2? Do you know that one?
Nope.
Good. And don't go looking for a calculator. Leave it. How about the square root of 3? Do you know that one?
Is it 1.5?
Nope.
Nope.
If you don't know it, leave it. Do you know the square root of 4?
2.
And what is 2 over 2?
1.
This is your multiplication chart that you guys need to memorize from here on out. Now remember, these are complements of each other. They're cofunctions. So notice that the 60 for sine is root 3 over 2, which means what would it be for cosine? Cofunctions, complementary. 30 and 60 together is 90. There's your root 3 over 2. Same ratios, values for the sine of 60 and the cosine of 30. That also works for 0 and 90. Notice we got a 0 here and a 0 there. Same values. So I'm just going to write them down. 0, 1/2, root 2 over 2, root 3 over 2, and 2 over 2, which is a 1. And you guys may be wondering, well, hey, what about the other of the big three? What about the third? Can't forget about the third child. What about tangent? What did we just get done defining tangent to be? What over what?
Sine over cosine.
And if we know what sine over cosine is for each one of these angles, then don't we know what all of these values are right below it? Done. Then all I got to do is label them. Now careful, we know 0 over 1 is what? Good class, 0. All right, what's the next easiest one? Do you know what 1/2 over root 3 over 2 is? Me neither. But what about root 2 over 2 over root 2 over 2?
1.
Beautiful. Then I know that this is a 1. So I got 0 and then skip that, a 1 for 45. Those are two of my favorite for tangent. Root 3 over 2 over a 1/2. Nah, I don't know that yet either. What about 1 over 0?
0.
So Samara, if you have one pencil that you're taking notes with right now, do me a favor, take it and divide it 0 ways. We can take nothing and find what it's equal to. You can take nothing and divide it any number of ways. I could divide it all 10 ways between us and we'd all get nothing. But if I have 10 things and I try to divide it 0 ways, that doesn't make sense. Here's why. If I set this up as an equation, let me prove it to you real quick. All I'd have to do is multiply over by a 1, right? To both sides. Let me rewrite this a little bit better. And if I multiply this 1 over here to get rid of it, whether it's 1 or 4 or whatever, right? If I multiply both sides by 4, then that cancels out. And I get 0 equals 4 times something. Well, what would that something have to be in order to be equal to 0?
0.
Exactly. Then we know that our answer to this is 0. But if I try to do that same thing over here, right, what would I have to multiply by over here? I'd have to multiply by 0 to quote unquote cancel these out, which is kind of weird. I don't even know if I can take nothing and divide by nothing and it becomes 1. But let's just say it worked and I get 4 times something and 0. Well, something times 0, is that ever going to give you a 4?
No.
So that's why we can never divide by a 0, which means what do we put when we have 1 or any other number divided by 0?
Undefined.
Very good. Excellent, Luis. That means it is undefined. We don't know. We don't have a value that works for this. Kind of weird. If you guys did some of that homework, you saw in those quadrantal angles, we ran into some of those problems where there was a 0 in the denominator. And therefore, that's when your calculator gets upset at you, right? You put in the tangent of 90, it's going to go error. It can't do it because it's undefined. Okay. Last few things here. How do we do those? Well, we just take what we know. We have 1/2 and we're trying to divide it by a √3/2. Or we have a √3/2 and we're trying to divide it by the 1/2. Which one do you guys want to do first?
Doesn't matter.
I agree, but this one looks easier because it doesn't have a root in the denominator. So I'm going to go ahead and multiply by the reciprocal of the denominator, which is 2/1. And that is my fancy 1 that I'm multiplying by to get something that's equivalent, but looks a little different. 2's cancel, and so do these. So all of these became 1s other than what? The √3. So in this one, I'll have to do something similar, and I'll have to multiply by the reciprocal to get this all to cancel to be a big nasty 1. The 2's here also cancel again, but I'm left with this. Anybody recognize that again? That's the √3/3 problem that I had you guys do at the very beginning, week 1. So my other value that I get for tangent is √3/3. So those are the 2 special values. Otherwise, for tangent, we start at 0. At 45, we get a 1. It's my favorite 1. Little pun there. And then at 90, straight up and down, it's undefined. Remember, I told you with the 30, 60, 90 triangles, we're going to have the √3s involved. And because 30 is smaller than 60, it's going to have the divided by 3 to be smaller. Where in 60, it's bigger, it's going to be the bigger angle, just the √3. Okay, so I wanted to show you guys how to build this, but do I want you to have to set this up and build it every single time just to figure out what the cosine of 60 is? No, I want you to memorize all of these so that when I ask you what the sine of 30 is, you all say what immediately?
1/2.
Beautiful. That's the goal. Just like what 7 times 8 is.
50. Oh, yeah, 56.
Very good. And until you memorize these, I'm going to keep hounding you on it. Okay? That's all I got for today. If you guys want to stick around, I'll be at my office hours. All right? And feel free to come in and finish that group quiz that some of you guys got close to finishing. Okay? Have a good one. Thanks for coming. I'll see you all next time.